Hey guys, welcome back to chapter 17. We're going to take a little bit of a turn away from rate laws, integrated rate laws, and talk a little bit more about how reactions actually take place. So one of the cool things about kinetics is not only does it tell us about rate or speed of reactions, but it also tells us about how reactions actually occur. So we are just going to simply scratch the surface of this. You'll get much more details about how reactions occur in organic chemistry and beyond. But let's at least scratch the surface today of how reactions take place. So we're going to use the platform of something called collision theory. Collision theory states that reactants must collide in order to react with one another. So they must first and foremost collide with one another. They've got to be in the proper, what we call orientation when they collide. So for example, in this reaction, A and B are switching places. So it was AA, now it's AB. So when they collide, the A has to collide with the B in order to kind of knock it or change places with it. So it has to be in the correct orientation. And then there has to be adequate kinetic energy in order for that collision to do anything, right? So we can't just simply kind of accidentally brush up against each other and expect a chemical reaction to take place. There has to be some sort of energy associated with that collision in order to rearrange those elements. So that's going to be the collision theory, the platform that we stand on moving forward. So if that's the platform we stand on, it has to collide with the correct orientation, enough kinetic energy. The speed of a reaction is going to depend on three things, really. We talked about the first one at length so far. So rate depends on concentration. The last two we're going to talk about in the next kind of series of videos is how rate depends on structure and orientation, and how rate depends on temperature. Before we move past the concentration, let's just really quickly kind of summarize what we're saying here. So the first half of this chapter, the rate law, the integrated rate law, talked about the concentration of the reactants. And typically, as the concentration of reactants went down, most of the time the rate also decreased. So the more number of particles, the higher the concentration is. Typically, that would lead to more collisions, which would be an increased rate. As some of those reactants disappear, there's going to be less particles and therefore less collisions occurring, which is going to decrease the rate of that reaction. For the remainder of this video, we're going to talk about this idea of how structure and orientation affects the rate. So as I alluded to, when these chemical reactions take place, they have to collide in the correct format. Okay. So what I see here is the following chemical reaction. So we're going to have carbon monoxide reacts with oxygen, O2, to produce carbon dioxide and then just an oxygen atom by itself. Okay. If I look at this CO2 that forms, I look at the chemical structure of CO2 as oxygen, carbon, oxygen. Okay. If these two molecules, the carbon monoxide and oxygen, were to collide, and the oxygen from O2 were to come into contact with the oxygen from carbon monoxide, we would not have a reaction form. That collision would result in something that looks like this, and that's not the carbon dioxide that we're looking for. Okay, so when this collision occurs, the oxygen from oxygen has to collide with the carbon from the carbon monoxide. When this collision happens, and if it happens with enough energy, what we'll see is this oxygen will create a bond with carbon and break its bond with the other oxygen. So we'd see CO2 formation, and then that other oxygen kind of float away. So if orientation of particles is so important, are there ways that we can manipulate how molecules are oriented or structured to kind of facilitate or speed up these reactions? So is there something that I can do to speed up the reaction between carbon monoxide and oxygen? And there is. So there's something called catalysts. So catalysts are chemicals that are not consumed during a chemical reaction, but affect the reaction rate. They speed it up, right? So chemicals that are not consumed. Catalysts are something that are just going to kind of exist in the environment where the reaction is taking place. We utilize it to do the magical chemistry, and then it gets kind of released to exist in that environment again. So it's not something that is used up. It's kind of an endless supply. It gets recycled. Okay. So here's the chemical reaction that we're going to look at. So ozone, this should be a subscript 3. So ozone reacts with oxygen to produce 2 moles of oxygen gas. Okay. This is the chemical reactions that we've looked at for the most part. But as it turns out, chemical reactions don't always exist as just like, here's one step. Typically, chemical reactions happen in a series of steps. So that's something that we're going to see more and more this chapter. So the series of steps that happen for this chemical reaction in combination with the catalyst are as follows. So chlorine in this case, or chlorine radicals, will catalyze the decomposition of ozone. So having those chlorine radicals in the atmosphere will speed up the decomposition of ozone. And here's how that happens. So ozone will react with those chlorine radicals to form this ClO complex. This reaction readily or very speedy happens to this. Then we'll see that ClO complex will react with another oxygen atom, just as kind of in the environment, to produce that second oxygen gas, and we see that the chlorine gets released. So let me get some terminology out of the way, and then we'll dive a little bit deeper into what's going on here. So first, what we see is our intermediate steps. So these 2 steps that we see are what we call intermediate steps. They're steps that happen that when we add them together, when we look at them as a whole, they add up to the overall reaction. In the intermediate steps, we see a couple things that we want to label. So first thing I see here is chlorine was just kind of existing, was there. And then chlorine gets released as a reactant later on. So we consume it, then we release it. This is our catalyst. So something that is not consumed but does speed up the reaction. Another thing we want to identify, just some terminology to get out of the way, is this guy right here. So this is kind of the opposite, where we produce it in one step, and then we immediately consume it in another step. So we produce ClO, then ClO reacts with something else. So produce, then consume. This is called an intermediate. When we're trying to get to the overall reaction, we're going to add these 2 intermediate steps together. It's important that we identify catalysts and intermediates because they do not show up in the overall reaction, right? We use it, then we release it, or we produce it, then we consume it. It's not part of the overall reaction. So now looking at my intermediate steps, I want to add them together. So I'm going to add together anything that's left on the reactant side. So I have O3 and I have oxygen. And then I'm going to add together anything that's left on the product side. I have O2 and O2. So I have 2 moles of that oxygen gas. So what we see here is we add together our intermediate steps to get to our overall reaction, not including catalysts, not including intermediates. So what is the purpose of the catalyst? Why are we studying this? Well, the catalyst provides an alternate mechanism or alternate way to react, okay? If it was just this reaction path down here, O3 plus O, that would be a much slower reaction. But if we introduce this idea of a catalyst, it's going to speed up that reaction by breaking it down into 2 steps and making it a faster reaction. Here we see something called a reaction energy diagram. So this is just going to be a pictorial representation of what catalysts do. So let's talk about what this diagram means. So over here on the left is the beginning of our reaction. Over here on the right is as our reaction progresses. So left to right, reactions progressing. From bottom to top, that's going to be the energy associated for this chemical reaction to take place. So the first thing we see here is our reactants. Our reactants are fairly high in energy. They're about halfway up this graph. And then over here we see our products. Our products are much lower in energy. But in order to get from our reactants to our products, we have to go through this high energy transition state. So we've got to kind of climb or surmount this hill in order for that reaction to take place. Now the blue path is the uncatalyzed path. So if we went just from oxygen or ozone and oxygen reacting, we would have to surmount this really big hill. Once we got to the top of it, then we would get our products. The red represents a catalyzed pathway, so that like 2-step process. And what we see is there's still this kind of transition state where there's still a hill we have to go up and over, but look how much smaller that hill is. So we have to go over this teeny tiny hill, use our momentum for the second hill, and then we get to our products. So it lowers this kind of energy associated with the reaction taking place. So catalysts provide an alternate mechanism or a different way to react, and that alternate mechanism is lower in energy. That's how catalysts speed the reaction up. Let's take a look at an example. Acetaldehyde, which is this guy right here, can undergo catalytic decomposition according to the following mechanism. I want you guys to identify the catalysts and intermediates and then determine the overall reaction. So each of these is an intermediate step. So identify catalysts and intermediates and then add together what's left to get the overall reaction. Alrighty, so first get my color. So catalyst. Catalyst is going to be something that is just kind of there, and we use it as a reactant. And then what we'll see is later on in a later step, it gets released as a product. So my catalyst in this case, we've got 2 reactants that we start with. This acetaldehyde doesn't get released, but iodine does. So we use iodine in the first step, and then we see we produce it or release it in the second step. So this is our catalyst. Our intermediates are kind of the opposite or the inverse of that. So intermediate is going to be something that we create, and then in the very next step, we consume it or destroy it. So in the first step, I create CH3I, I create HI, I create CO. Looking at the very next step, I consume CHI, and I consume that HI. We've got two intermediates here. So we produce it and then immediately consume it. These are intermediates. Now lastly, we want to determine what is the overall reaction. So the whole purpose of identifying those things is that they do not end up in the overall reaction. Okay. So now I'm just going to add up everything that's on the reactant side, everything on the product side. So I've got this acetaldehyde. Writing over there, it's the only thing. CH3, CHO. So that's on the reactant side from the first step, nothing left from the second step. And now we go to our product side. So we've got carbon monoxide from our first step, and then the CH4 from the second. So this is a very good indication of a problem that may be asked on the test, where I give you intermediate steps, and I say identify catalysts, identify intermediates, and then give me the overall reaction. Before we complete our thought on catalysts, I want to give you just kind of a couple of tangible real-life examples of catalysts that you're probably a little bit familiar with. So the first one is a catalytic converter. Now you know where that name came from. So the catalytic converter acts as a catalyst to break down or to speed the conversion of nitrous oxide, very pollutant, to nitrogen and oxygen. So what the catalytic converter does is it holds that NO in place to promote the rearrangement. So it's going to hold that nitric oxide in this kind of very handy format so that the nitrogens line up, the oxygens line up, and we can get this rearrangement. So the nitrogen-oxygen bond breaks, the nitrogen-nitrogen created, oxygen-oxygen created. So the catalytic converter holds the molecule in a very specific orientation to speed up the breakdown. What happens is it is absorbed into the metal, and then it's kind of moved around until it reacts. And then after it reacts, it gets released. Catalytic converters are made of metals like platinum or radium, so they absorb this and then they're able to release it once it's been converted. Another place that you'll see catalysts is in biochemistry or biology, things like enzymes. So enzymes are little sites within a cell, within tissues, wherever. And those sites have a very specific shape or orientation. So what happens is some sort of substrate or some sort of molecule will come into that active site. Once that molecules are locked into that site will move, or it'll release a chemical, or any number of ways that enzymes work. So it promotes that kind of breakdown of that molecule. And then once that molecule has been broken apart, the products get released. So enzymes are examples of catalysts. They speed up the breakdown of different molecules in our body. So here's just an example of a catalyst. Obviously, a catalyst does not look like this with hexagons and octagons, but you'll get the idea. So if this is our sucrose molecule, so sucrose is essentially glucose, fructose attached with this bond here. If the sucrose comes into the sucrase enzyme, so this enzyme has one job, and that's to break down sucrose. So our sucrose comes into the sucrase enzyme. What happens is this active site then twists or opens just a little bit, which is enough to break this bond. And then what gets released is glucose and fructose. So taking a complex carbohydrate and breaking it down to a simple carbohydrate so that our body can use it for energy. Here's an example of what that sucrase enzyme looks like a little bit more realistically. So that sucrose molecule comes in, and what happens is this right side and this left side open up just a little bit. And that opening up breaks this bond, it strains the bond, weakens it, breaks it, and then glucose and fructose can get released. So that is discussion of catalysts and how they speed up chemical reactions. I hope you guys found this helpful.